Should we get started, Keely?
Yep, works for me if Oscar's ready.
Yep, whenever you want.
Okay. Good evening, everyone. Thank you for attending and welcome to our virtual presentation. My name is Doug Pelletier. I'm with the University of Illinois Civil Engineering and Environmental Alumni Board. This evening, we have the pleasure of Professor Oscar Lopez-Pamies. He's going to give us a nice presentation, as you can see here on the screen, Emerging Smart Materials. After his presentation, we'll do a little Q&A session. I think what we're going to do is we're going to have folks submit via chat that they want to ask a question, and then I'll just follow that chat to give people an opportunity to talk through their questions. And with that, I will turn it over to Professor.
All right. So, well, thank you so much, Doug and Keely. It's great to be here. And well, I'm excited to tell you about some recent work, I suppose, over the last, 4 or 5 years on, as you can see here, materials. So mostly I'm going to talk about, fracture properties of materials, but I will tell you about 2 other things. So this one here, I thought that I start by taking a step back and, taking an overarching perspective, how technology or the advancement of technology typically hinges on the availability of new materials, materials that can do things that, we couldn't do before. I mean, obviously not every technology that we benefit from is based on the use of new materials, but most of them are. So I thought I'd include some basic ones that, are familiar to all of us. And so I think it's difficult to overstate the importance of concrete. And, Portland cement was invented in 1824, and all of us know what that has done for us and continues to do for us. Another example, very classical one, rubber was invented in 1844. Charles Goodyear discovered cross-linking back then, or at least that's when the patent was filed. And this is just one example, but there are many, many examples where elastomers are being used and are being, able to enabling new technologies. Asphalt is another one. This is the road from Forrest Gump, by the way, if you recognize it, famous road. So this is just, one example again that is very familiar to all of us. And maybe a more modern one is Gorilla Glass, which was invented in the 1950s. But, with iPhone, it's the application of it became, more pervasive, and, it's really everywhere. So here I will add, et cetera, et cetera, et cetera. So these are just examples that illustrate this key point that in order for us to advance technology, typically we need new materials, right? Or materials that are able to do things that we couldn't do before. So this is really the driving force of our research, right? So all of these examples have to do with mechanical properties. One can focus on other properties, electrical properties or magnetic properties, right? But the examples that I showed you before dealt with mechanical properties. So in today's lecture, I'm going to mostly focus on mechanical properties, and in particular on fracture. And I thought that it would be, fitting to be careful and define what do we mean by mechanical properties, and in particular, more generally, what do we mean by mechanics, so that we are all on the same page. So what is mechanics, right? What is the thing that we're after? What is the behavior of materials that we want to understand and exploit to advance new technology, to enable new technologies? So, like with anything, one probably should start with the definition, and I'm going to call that the clinical definition of mechanics is the study of forces and deformations in matter. So I'm going to show you a few pictures, and all of us can relate to them, and that's what mechanics is, really. If you go to Merriam-Webster or any other dictionary of your choosing, that's the definition that more or less you're going to find. But to actually truly understand mechanics in a deeper way, one can come up with more exotic definitions, and I'm going to go over 3 other definitions, and this is going to help us to understand at a deeper level what we mean by mechanics and why it's of interest to study. So the clinical definition, the study of forces and deformations in matter. These are just a few examples. This is me stretching a rubber band. I'm sure many of you do this, maybe even daily. So this is just a very relatable problem where, you know, you take a structure made out of some material, you stretch it, you deform it, you apply forces, it deforms, right? Mechanics is about understanding this process, right? Forces applied to matter induce deformation. And then, of course, we can think about anything that is made of matter that is subjected to forces, which is pretty much everything. This is the Eiffel Tower. This is, you know, with some artistic license, highly deformed, just to drive home this idea of deformation. Of course, the Eiffel Tower hopefully doesn't deform that much, but it deforms quite a bit. When I was young, I used to play tennis, so I like this picture just to drill down this notion of deformation and forces. This is high-speed camera of you know, what happens when you strike a tennis ball, which is a spherical shell, with a tennis racket, and you can see the very significant deformation and complex deformation that takes place. And one thing that I'm going to focus on today is when you subject matter to exceedingly large forces or exceedingly large deformations, matter may fracture. You know, may crack it, and then the structure breaks. I included 2 pictures here. This is happy fracture. This is what you're supposed to do when you buy a yacht, you break a champagne bottle. I wouldn't know. And this is a less happy fracture, right? This happens quite often, right? So this is just examples that, you know, the structures are everything, and at some point they may break. I'll come back to this point later. All right, the second definition is related to why more clearly why we want to study mechanics than the first definition. So we can think of mechanics as a time machine, and we can think of any theory, if you like, as a time machine that allows us to go to the future, right? If we have the equations that describe the mechanics of structures, certainly we can predict the future. We can figure out how things are going to behave before they are built, right? How things are going to behave under any circumstance, and that's why, you know, we use mechanics to design whatever it is that we want to design. So we can think of mechanics as a time machine, and this is just a couple of examples, you know, to illustrate this idea. So this is an experiment on a perforated plate. Perforated plates are used in many applications, and you have some cantilever boundary condition here, and it essentially deflects because of gravity. And then we would like to understand, we like to predict how very precisely this structure deforms, and this is a simulation. And as it turns out, this is not entirely trivial. However, we now have the equations and we know how to solve them, and therefore we can predict precisely how this is going to behave before we even build it, right? And actually the simulation came before the experiment. So it's a time machine. This is another cool one, you know, like, okay, so we have a dome and you throw a projectile, and the natural question is, okay, is it going to break the dome or not? In this case, it does. And can we predict this? Can we predict the force required to break the dome? And if you break the dome, what is going to happen? How the structure is going to shatter, for instance, right? So this is the idea. The idea, if we have this knowledge, if we have a theory, a set of equations that describe how structures behave mechanically, we can therefore predict the future. We can design structures for any purpose. So that's the power of thinking about mechanics in this way. Another very important aspect of thinking about mechanics as a time machine is that if certainly we can go to the future, we can travel to the past. And this is nothing but forensic analysis. So, you know, whether we like it or not, accidents happen, and we need to figure out what went wrong so that it doesn't happen again. This is a collapse of a bridge not far away from here, the Interstate 35, next to the University of Minnesota in 2007. the bridge collapsed and 13 people lost their life. And there was a huge investigation, of course, as there's always an investigation in these cases to figure out what went wrong, to see if there were other bridges in danger of meeting the same fate. And it turned out after a year and a half that they figured out what went wrong. And what went wrong is one of the gusset plates was buckled during the if you like, fabrication of the bridge, when the bridge was put in place. And it was this buckle gusset plates that gave way and actually resulted in the collapse of the bridge. And this was possible because, as you can see here, this is a simulation. This was possible because we have the equations of mechanics for this structure, for this material, for this steel in particular, and therefore we can actually accurately, with equations, determine how this behaves. And that's how we can use these equations or this theory to go to the past and do some forensic analysis. All right, this is my favorite definition. So I went through two of them, right? The clinical definition, time machine, now a philosophical definition. When one thinks about mechanics, it is, we can argue rather philosophically that mechanics is the inescapable science of everyday life. And what I mean by that is that we are constantly surrounded by mechanics. And here are just a few examples. I'm not going to go over all of them, but just I guess I can go through one of them. You can read the others. Every time we take a breath, our lungs deform, they inflate, they deflate, right? That's mechanics right there. And everything that's around us is made of matter. Matter deforms when subject to forces, and that is exactly mechanics. So it's really truly we are surrounded by it, and that's why it is to our advantage to understand it, right? And then finally, the definition that is going to get us going with fracture and the things that we've been doing is what I call the culinary definition, right? So mechanics can be really thought about, can be thought as cooking, right? With 4 ingredients. So there are 4 ingredients. These are them: geometry, deformation, forces, and material behavior. And this explains what I mean by this, right? If you think of your favorite structure, anything that is made of matter, you can think of something like the Eiffel Tower, if in a typical structure, or you can think, the human heart. Anything that is made of matter occupies a domain in space. So that defines its initial geometry. That is ingredient number 1. This initial geometry deforms. And think about the rubber band. You apply forces, which is another ingredient. The structure with initial geometry deforms. And how it deforms depends critically on what material the structure is made of, right? So we can think of these 4 ingredients one at a time separately. And as it turns out, we know now, we have understood completely, fully, the first 3 ingredients. There is nothing that we do not know about how to describe geometry, deformation, and forces. There is, however, an ingredient that we, even though we have made quite a bit of progress, we really don't understand, not even close, right? I mean, this is where all the research is taking place. That is the 4th ingredient, material behavior. How do we describe, with equations, if you like, or with experiments, if you like, how do we describe in a quantitative manner how matter behaves mechanically? When you subject it to an arbitrary load, can we say very precisely in a quantitative fashion how this piece of matter is going to behave, right? And that is actually some difficult problem. And I'm going to be telling you a little bit about that, focusing on fracture, which is particularly challenging. All right, so with that preamble, let me tell you what this presentation is going to focus on. It's going to focus mostly on the mechanical properties of solids that we use for structures. And in particular, we're going to look at the fracture properties of solids. And as I mentioned, this is challenging and it's going to become apparent. I'm sure it's already apparent when you think about things breaking, right? Then I will tell you a little bit about some of the directions, these are different properties. So I'll tell you a little bit about solids that contain liquid inclusions and why these are very exciting materials and what is that we can do with them, right? So these are the two examples. And finally, I'll tell you about a new program that is related to all of this that we have just started this semester here in the department, the EMA program. All right, so the pervasiveness of fracture, I couldn't help myself. So I'm gonna include again some pictures, but I really shouldn't, right? Because fracture is so very pervasive and it's so very familiar to all of us that it's, it really doesn't need an introduction, but still, I couldn't help myself. And I included the following. So Benjamin Franklin famously wrote to, a friend of his in Paris. He spent a lot of time in Passy next to Paris, some sort of ambassador. So in 1788, the US Constitution was ratified, and soon later, Benjamin Franklin wrote the following that has become famous, right? Our new Constitution is now established and has an appearance that promises permanency. But in this world, nothing can be said to be certain except death and taxes, right? And then this took off, and then of course we use this in many occasions, even now. So more than 200 years later, in hindsight, one could argue the following amendment: nothing is for certain except death, taxes, and fracture. And indeed, everything breaks, right? And this is something that is exceedingly important for us to understand. And when I mean by understanding is quantitative understanding, very precisely. So I already showed you these couple of pictures, right? Happy fracture, maybe not so happy. And this is certainly the other extreme of happy, right? Accidents happen. This was fracture of a bridge. 6 people lost their lives in this accident because of cracks in this building, in this bridge. This was, I think, Florida International University in Miami. So, but these are just 3 examples, right? I mean, you can think of infinitely many more. So fracture is an exceedingly important aspect that we truly want to understand. So what I'm going to show you is what is our current understanding of fracture. We have recently developed a theory that allows us to, we believe, to predict everything in terms of nucleation and propagation, at least in some classes of materials, if you like brittle materials, but not only. And then I'm going to tell you what is that we can do with this knowledge, right? And how this can be used. All right, so I don't want to be too technical, but I thought that would be important that I go over how did we develop the theory and what is that, the steps that we follow to get there. So for that, I'm going to kind of show you what is that we know from experimental observations about fracture. And of course, you can imagine that this is, something that has been reported over many years, and in fact, more than a century. So I will tell you about the key aspects that, the key features of fracture. And then I will briefly show you a theory that supposedly can predict all those observations, and therefore something that we can use to design or do forensic analysis or whatever. Then I will show you a couple of applications, and then finally something else. I mean, how do we use this theory to design new structures that are optimized in some sense to crack resistance? All right, so the first view of fracture. So you may be familiar, there is a classical book by Love that was published at the end of the 1800s on elasticity. And it is there that there's a chapter where it is very nicely summarized what was the state of the art at the time about fracture. And just to put things in perspective, again, from a historical point of view, the notion of stress was introduced by Cauchy in 1823. So soon after, people started to, now that they had a clear understanding of stress in materials, stress in structures, they started to think about, okay, what happens when things break? And then, pioneers like Lamé, Saint-Venant, and many others, they started to postulate that if you take a piece of material and you subject it to tension, there is a critical stress at which the material is going to break. And then some people say, no, that is not what happens. What happens is, and when you do that, there is a critical strain, right? A critical deformation at which is going to break, and then and so on and so forth. All of them actually were partially right, in a sense. And you can do this experiment yourself and ask, okay, when the rubber band is going to break when I simply subject tension, this is what happens, right? At some point it's going to break. This happens to all materials. So all these notions are essentially correct. And this notion is the notion of strength. There is a critical value of stress at which the material is going to break, and that is characteristic of the material. However, they realize that this is great if there is no singularities in the structure. If you start to consider structures with sharp corners or with cracks in it, these fail miserably. And the reason being is that if you have a geometric singularity in a structure, this implies that the stresses are infinitely large at the singularity, right? If you think of a corner that is sharp corner, the stresses there, the moment you touch it, are infinitely large, which would imply that it should break right away, but that is not what happens, right? So this idea worked, but only worked partially. So this was in the 1800s. Then along came Griffith, 1921, several decades later. And then he said, actually, strength is not what happens. What happens is a competition of energies. If you take a piece of material, the material may fracture or not, depending on a competition between energy of deformation and energy that is associated with the creation of surface. And actually, this works great, but this only works great when you have a crack in the specimen. So this is, think of a tape, think that you are going to cut it with scissors and therefore put a crack. This is a very singular feature, geometrically speaking. And when you pull on it, at some point, the crack is going to run. And Griffith explains this. So this is great, except that it's not so great because it's not explaining the previous case that I show you about strength, right? If you apply a force to a piece of material, let's say tension, it does not follow this. Fracture will not happen according to Griffith, it would happen according to strength. So essentially what we have in this 1921 year is that, well, we have two limits. What happens to a structure that has no singularities, geometrically speaking, that is the strength. What happens to a structure that has a crack in it, that is Griffith. And unfortunately or fortunately, the field of fracture focused on Griffith's idea, and for 80 years, that's where most of the work has been done, right? But now, when we started to look at this problem, we, wanted to look at the whole picture. And so here I'm going to show you the whole picture, and I'm going to tell you where things stand now. All right. So in reality, if you think of structure, the following may happen. You may nucleate in the bulk, right? Think of this as, I don't know, some sort of beam with a fancy geometry. It is possible that you will create a crack because of the loads that you apply to it in what we call the bulk, away from any geometric singularity. But you may also have a large crack or many large cracks to begin with, right? Due to the manufacturing process, you may have cracks in the structure. So, well, you have to account for the fact that you may nucleate from a pre-existing crack, or you may nucleate from the bulk. And, more generally, you have to take into account that you may have corners, which are also geometrically singular, but not as singular as a crack singularity. And you may nucleate a crack from there, or you may have a rounded corner, which is not sharp, but the geometry is changing very rapidly, and you also may nucleate from there, or you may nucleate from the boundary. that is smooth, right? All these things have been observed to happen. So what we now need to think about is, when we think about fracture nucleation, how is that we describe the entire picture? How do we account for the fact that nucleation of fracture can take place and in many different ways? So bottom line is the following. What we know now from experiments is that nucleation in the bulk is controlled by the strength of the material. Nucleation from large pre-existing cracks is controlled by the fracture energy, or if you like, Griffith, right? These are the things that I showed you before. These are just experimental observations. And then anything in between really is a transition zone. It's like there is a mediation between these two limits. So we should think about this as two limiting cases. Anything in between, it's an interpolation between the two. And this has to do with fracture nucleation. And then, of course, after nucleation, you may have propagation. All right, so this is a bit more, detail about what is the strength. A strength can be described as a surface in stress space. So if you take a structure and you subject it to a uniform stress, at some point it's going to break. But the stress is, okay, I'll use the terminology, it's a tensor. It's a quantity that is not scalar. It has many scalars in it, right? And you have, let's say, 9 scalars. So you need to worry about whether you do tension or shear or a combination of other things. And that means that actually what you have, strength, is a surface. Much like a yield surface, you have a strength surface. And people have done experiments, especially in ceramics in the 70s. And I'm going to show you, some data. This is Titania. And you can see that these are tubes that were pressurized and then extended. So the state of stress is multi-axial, and they develop cracks within the bulk at different states. So this really tells you that what you're dealing with here is a surface in a stress space. And this is just a characteristic of the material that you need to account for because this describes how fracture nucleates in the bulk. Then from a large persisting crack, now this is well known, and this is Griffith fracture. By large, I guess I'll point out to the following, materials, when you look at them with a microscope, they have defects. What large means is that this crack has to be much, much larger than the inherent defects. And if that's the case, we know from experiments when the crack is going to propagate, when it's going to nucleate from the crack front that is pre-existing. And this essentially is given by this formula. If you're familiar with it, that's fine. If not, it's a different criterion, that the strength criterion, right? And this is, again, this is well known from experiments. And then, of course, you have the intermediate region, and this is also well known from experiments. This is experiments on alumina, which is a ceramic. And so these experiments were done on a specimen where you have a crack, a pre-existing crack, and you see here the crack size. If the crack is big enough, the critical value of the load that you apply at which the crack goes is controlled by Griffith. Griffith is this diagonal line. As you make the crack smaller, right? This is an initial crack. You make many specimens with a smaller and smaller cracks. You see that you have a transition from Griffith to strength. Strength is the horizontal line. What is happening here, it's very clear. You're making the crack smaller, and by making it smaller and smaller, you're making it comparable in size to the inherent defects that you have in your material. It is the inherent defects that control the strength of the material, and that's why you get a transition from Griffith fracture to a strength fracture. All right, so this is what we know from experiments, and all there is for us to do is, well, the propagation of fracture is also Griffith. This we know from experiments, so we know nucleation, we know propagation. So what we need to do is to realize that if we hope to have a complete theory where you look at a structure which possibly may contain pre-existing cracks, corners, or whatever in arbitrary geometry, and you subject it to arbitrary loads, can we write down equations that will tell us under general scenario of loads and geometry when fracture, when cracks will nucleate, and how they will propagate. And from the experiments, we know that if we have hopes of developing such a theory, there are three basic ingredients that one must account for. Those are the elasticity. Let's say we're going to talk about elastic materials, the elasticity of the material, the strength surface of the material, and the so-called critical energy release rate, right? So this controls elasticity. It controls also the competition with nucleation and propagation of large cracks, and the strength controls nucleation in the bulk. So in addition to these basic ingredients, the theory that one has to develop has to account for an interpolation between strength and toughness. And so that's, again, that's just from experimental observation. All right, so I'm not going to go through the details of how we develop such a theory, but here is one such theory. And obviously, many things were done before us that we benefited from. And I'm pointing out here the great work of Gilles Frankfurt and Jean-Jacques Marigot in '98. But that in itself is incomplete, needs to be generalized. And this is what the generalization looks like. So I don't want to get, again, there's no point here in talking about the technicalities, but the message is that now we have equations that take as ingredients the elasticity of your material, whatever that may be. It takes into account the toughness of the material, whatever that may be. Those things are measurable from experiments. And this quantity here takes into account the strength. So all these ingredients that are absolutely necessary to have a complete theory enter here. And then we can go and see what the theory predicts. And we have done comparisons with many experiments on many materials. And so far, everything has checked out. And it seems to indicate that these equations may indeed provide a complete theory for the fracture nucleation and propagation, at least in materials that can be considered elastic brittle. All right, so I'm going to show you. A couple of examples, and Doug, please keep me honest with the time. I'm going to show you a couple of examples that are very challenging, and you can see what the theory is predicting. One of them is indentation of glass. So think of, I don't know, bulletproof glass. How is glass made bulletproof? Or think of, these hammers that, you encounter in trains. So if there's an emergency and you need to break the glass to exit, you have these little hammers with pointy, right, tips that are supposed to allow you to break the glass, right? So this is the kind of problem that we're going to be looking at. Another problem is, think of your, I don't know, car tire. Car tires are very fancy structures. Essentially, they are made out of particles, carbon black. That's why they're black, embedded in rubber. And what happens is that there is fracture that takes place inside this, right? This is just two examples to illustrate, how the theory fares with reality. And I picked these two because they are particularly challenging and because they have not been explained until now. All right, so, back in the 80s, Mougineau and Mougis made some careful experiments and where they were controlling what type of glass they were indenting. And so these are, the details of the geometry and the indenter. All right, so they take a metallic indenter and they apply a force. And what happens is this. At some point, if the force is sufficiently large, cracks nucleate as ring cracks. And if you continue to apply load, these ring cracks then turn and they become cone cracks. And this is how fracture nucleates and propagates in glass due to indentation. So what people have understood and for decades actually now is that if they know what happens in terms of nucleation, if they take this as given, propagation, they already know that is controlled by Griffith, right? And again, once you have a pre-existing crack, Griffith will tell you what happens with the propagation. The problem has been always, okay, how do you nucleate the crack? And that is a challenge. How do you have a theory that gives you nucleation, right? So when we run our theory, this is what we get. This is half of the specimen. This is a simulation. And these colors here are indicating the presence of a crack. So the theory says that at this value of the applied displacement of the indenter, you nucleate a crack. Indeed, you nucleate a crack. There is a ring crack, right? This, you should think of this as an axisymmetric specimen, right? So if you think about a revolution along the vertical axis, you will see that it becomes a ring crack. And this is what happens when you continue to push the indenter down. After you nucleate a crack, the crack turns and it becomes a conical crack. And these are just snapshots of what happened according to the simulation. So, okay, then we compare quantitatively. Qualitatively, this looks exactly as what happens in the experiment. And, you know, it is, you can see here that nucleation takes place on the surface of the glass, but not very close or, you know, directly below the indenter. The nucleation takes place away from the indenter at some distance. And the reason is that nucleation is controlled here by the shear stress, the shear strength rather, of the glass, right? That is what actually is being exceeded, and that is what triggers nucleation. It's not tensile strength, as many people believe. It's actually shear strength that controls nucleation. Once you have nucleation, up you go, you have propagation a la Griffith. All right, so we can compare with experiments. This is the critical force at which nucleation takes place for different radii of the indenter. And you can see here that we have quantitative agreement with the observations. Interestingly enough, here you can see that as you make the indenter smaller, the force required to nucleate a crack is smaller. And before I knew nothing about glass and I knew nothing about indentation. So this was very interesting to me that now I finally understood why in trains that you have a hammer and the hammer has a very pointed tip. And it's because if the area of contact of the hammer with the glass is small, the force that you need to apply to induce fracture, to nucleate fracture is small. But one has to be careful, because if you make the indenter too small, the indenter typically is made of a metal. The metal will have plastic deformation. That means that it will deform, the area will increase, and you will not be here, but you will be here. So there is a balance that if the indenter is not very strong and is going to have plastic deformation, you will never be able to break the glass if the indenter is too small, because it will deform and you will never break it. But if you manage to have something that is not going to deform, the smaller the indenter, the better, because a smaller force will give you nucleation. And once you have nucleation, the glass will just propagate the crack and you will break the window. These are other comparisons, quantitative for the location at which the ring crack appears. And this is for the propagation, right? The diameter of the cone crack and the angle at which the crack propagates. So all of them seems to check. And so we are pretty pleased with these comparisons because they suggest that the equations describe reality. All right, particle reinforced elastomers. This is another very challenging problem that has been not resolved for many, many years. And so I'm going to show you some experiments that we did with a collaborator in UT Austin, Ravi Chander, who's probably, I could say, arguably one of the best, if not the best, experimental mechanicians right now. So I'm going to show you a movie of the experiment. I'm going to show you the simulation of what happens. So these are glass beads. So you think of them as something very stiff that you embed in a matrix, right? So this is a typical, type of microstructure. I don't know, you can think of concrete, you will have aggregates in cement paste, right? It's typical to add fillers to a matrix that is softer. In this case, the matrix is an elastomer that is transparent. It's some sort of silicon. That's where you're able to see through, right? So this is actually the silicon. These are the glass beads or the reinforcing particles. They're very stiff compared to the silicon. So I'm going to play the movie. What we are doing to this specimen, right, is simplifying in the sense that you only have 2 particles instead of many, but they're very close to one another. You can see here the dimensions. So what happens is that you are going to nucleate a crack near one of the poles. That's a crack, but doesn't look like a crack because we are looking at the deformed configuration. So when you deform a penny-shaped crack, and this penny-shaped crack is between something stiff and something soft, it deforms asymmetrically. If we continue to apply the load, what happens is you have a secondary site of nucleation. And if we continue to apply the load, actually what happens is this crack is going to grow a lot and it's going to push this one away. So that is what happens. And then boom, that's a beautiful movie. And then what happens when you remove the forces is this. So these are still pictures of that movie. Essentially, you have nucleation, propagation, secondary nucleation. Then this secondary nucleation of a crack takes over, and this one goes away. Once you remove the forces and zoom out, you can see the particles here. And you can see that indeed, it's now a penny-shaped crack, right? We're looking at through the material. So this is nucleation within the bulb, right? And this happens in your car tires, by the way, all the time. But that's a different story. So you have healing, right? But I will not get into that today. This is just an example of, again, fracture nucleation in an elastomer that essentially is an elastic material that, and therefore is brittle. So elastomers, contrary to what you may think about the word brittle, elastomers or rubber are perhaps the most brittle materials on the planet, because they are able to deform elastically. And after that, they do nothing else other than create surface. They fracture. They do not undergo plastic deformation like metals and some other materials. So from that point of view, the elasticity is nonlinear. But other than that, they're perfectly brittle. All right, so let me show you the simulation. And you will see that what the theory is able to do, right? It's pretty much right on what happens in the experiment. So you have nucleation, propagation, secondary nucleation, and these are the stretches. Lambda is the amount of stretching that you're applying to the beads. And so here again, it's a very different material and a very different type of nucleation and propagation, but the equations seem to describe what happens in reality. This is just another one of the experiments. In this case, the particles are closer to one another, so you only have one event of nucleation. And because things are very close, the deformation is even more dramatic. It's conical and then becomes cylindrical, but this is nothing but a penny-shaped crack. All right, so these are just 2 examples. We have done comparisons with many other materials and many other geometries. And so far, everything seems to check. And so we're still working on that. But we are pretty encouraged about what we're able to do with these equations, essentially describe nucleation of fracture, propagation of fracture very accurately. So obviously, if that is true, one of the directions that one can think of is, okay, can we now design structures with optimized crack resistance, right? Now that we have these equations, we can use them to do whatever we want. And this seems certainly one of the directions that is exciting, right? Can we do structures that behave in a way that even in the catastrophic, case where they are going to fracture, they're going to fracture in a way that we want, right? So that we can control, if you like, we can control the catastrophe in some sense. So this is a collaboration with CE Professor Shirley Zhang, that we have a picture here. She actually has been working on topology optimization for a number of years. And this picture is in a building on campus, one of the newest buildings. And behind her, there are some beams with some holes. And actually, she helped design through topology optimization. Now, until now, what people have done in this field has been to design structures that are optimized, but only in elasticity, right? In this case, you are maximizing the stiffness of these structural members, in this case, beams. Now that we have a more general theory, the natural thing to do is to account not just for the maximization of the stiffness, but also to account or design, optimize how the structures, how beams or whatever behave if in the event that they were to fracture. And then you can think of several scenarios. I'm mentioning here 2 of them. Maybe what you want to do is you want to design structures that are going to perform elastically in some way, and they are going to delay the nucleation of fracture as much as possible. At some point, everything is going to break, but can we optimize that? Can we create a geometry, right? A structure with a given geometry that essentially is optimizing when fracture will occur. Alternatively, you may want to design a structure that, okay, this thing is may fracture, right? Cracks may develop. And what I want to do is develop a geometry that will absorb the maximum amount of energy through crack propagation. So when a crack propagates, when you create surface, you dissipate energy. So in an event of something collapsing, you want the structure to take as much energy as possible, so that people inside the structure doesn't take that energy, right? They don't take that energy. So that could be a different direction of optimization, and we are currently working on this project, and it's certainly very exciting. I guess I could show you. Let me do this. I don't know if you can see it, but she gave me things that she 3D printed, right? So this is a beam with some optimized microstructure, making use of the theory and topology optimization, and this is a tested beam, right? We are testing them to see whether what we expect is going to happen in terms of performance of fracture. All right. So let me go back here. Okay. Okay, very good. So very quickly, I don't want to be over time. I mentioned a couple of other things. That is as much as I plan to say about fracture. So let me go here. There. So another direction that I thought I mentioned, because it's pretty cool, is this notion of can we obtain or create new materials with some new properties by making use of liquid inclusions. And let me just remind you that typically when we have inclusions, again, think of concrete, think of a car tire, the inclusions that one adds conventionally to material to improve their properties are solid particles, and typically they are stiffer than the surrounding matrix. So there is this idea of, I guess I'll mention this example and I'll tell you about the idea of using liquid inclusions and why that may be beneficial. So this is just an example that shows that this is, again, I don't know, a piece of rubber. This is a so-called magnetorheological elastomer. So the matrix is rubber. It's not sensitive to a magnetic field. You can put iron inclusions in it. And this is an example of that. And then the idea that people were pursuing about 20 years ago or so, they say, okay, maybe we have an actuating system here. We can apply a magnetic field, and the thing is going to do something for us. And then maybe we can think of applications, right? And certainly people have thought of applications. It's nice to be able to actuate something with a magnetic field because it's a non-contact technique, right? You apply a magnetic field without touching the specimen. So what they saw is not much. This is an experiment where the magnetic field is very significant. It's more than 1 Tesla, which is a lot. And the deformation is very tiny. The reason is that iron inclusions are stiffer than the surrounding matrix. And by having them there, you do 2 things. You make the material sensitive to magnetic fields, but you also make it stiffer because the iron doesn't want to deform. So alternatively, one can think of if you want to have something that is sensitive to magnetic fields, you can use ferrofluid inclusions. These essentially are oil or a fluid, typically oil with nano iron particles. And this is sensitive to magnetic fields because of the iron, but it's a fluid, and therefore it deforms a lot. So if you run a simulation with ferrofluid inclusions as opposed to iron inclusions, you can get very significant deformations, which for some applications may be what you want, right? So the idea is with liquid inclusions as opposed to conventional solid inclusions, you increase deformability, or you may increase deformability. So the other aspect that is perhaps even more interesting is that when you have a fluid inclusion, then you have to think about that you may have interface mechanics. So think of surface tension, that they may play a role. In fact, there are experiments recently that show that interface mechanics for some systems with liquid inclusions control the entire mechanical response. And this is just one example. In this case, again, is silicon. These inclusions are glycerol, which is some sort of polymer, but it's a liquid. And let me just show you what happens. So this is indentation, again, of a block of material that contains liquid inclusions. And by changing the stiffness ratio, let's put it this way, by changing the size of the inclusions or the surface tension, you may end up with systems that are stiffer than the matrix, or they are softer than the matrix. So let me say that again. The inclusions are liquid, think of water. But if you make them small enough, the interface becomes stiff, because spherical, think of spherical inclusions, they want to remain spherical. And because of the surface tension. So when you try to deform them, they're going to push back, and they're going to result in a reinforcing behavior. Even though the inside of the inclusion is liquid and you can deform without a force, it is the fact that you have an interface that resists deformation what brings reinforcement. So you can end up with a very wide range of behaviors depending on what you do with the surface tension or the initial size of the inclusion, from softening to stiffening, and in fact, to what we call cloaking, right? These are simulations, comparisons with experiments. Cloaking means that you may have a system where even though you have inclusions, you have neither softening nor stiffening, but it would behave exactly as the matrix without the inclusions, even though the inclusions are being deformed. So what this is telling you is that you can actually cover a wide range of behaviors, from softening to stiffening to cloaking, by playing around with liquid inclusions, their sizes, and their interfaces. So now you can think that if you're going to make the inclusions ferrofluids or metallic liquid metal inclusions, that that's a very hot topic right now, you can start to explore all kinds of properties, and this gives us a way to really create materials with novel behaviors that, again, may help us enable new technologies. So with this, I will briefly tell you about the third item that I wanted to share with you, which is a new program that we have just started in the department this semester. It's called EMA, and you notice here a transpose. Okay, so it is engineering materials and additive manufacturing technologies. And of course, to make this fit, we needed to transpose the M with the A. Okay, so but it's EMA for sure, but EMA transpose. All right, so what is this? So as I tried to convey during the presentation, technological advancements happen mostly because we have new materials that enable us to do so. And therefore focusing on that, will allow us to, to go to the next generation of technologies. So I'm not going to get into these examples. I already mentioned these, smart materials that respond to magnetic fields, but there are many others. These are just some simulations of systems or where you apply an electric field. So I think with the things that I showed you before, I hope I made the point clear, and just to make it very clear that you can, the sky's the limit essentially. So our objective is to go from basic science to additive manufacturing technology. So essentially, can we create new materials with the properties that we want? And can we manufacture them to put them out there and, make it into the real world and make the world a better place? And this is just a couple of pictures of 3D printing of concrete, right? Something that some, of us are starting here. In particular, I wanted to show you, this is a movie credit to Professor Arif Masood, who actually has developed a course in additive manufacturing. And this is a 3D printed beam that is being subjected during this course, by the way, to compression, and you can see that fracture develops there, right? So these are the kinds of problems that we are thinking about, and I already show you, right, this optimization. So the idea is to really understand materials from a fundamental point of view, so that we are able to, create them through, advanced manufacturing techniques and use them. So I just point out that why do we want to do this? Well, beyond the fact that that's where my heart is, it makes sense because I think we are uniquely positioned. We in the department are about actually more than 15 faculty with expertise in material synthesis, modeling, testing, and 3D printing across all areas, not just in structures, but across all areas. And I think that makes us uniquely positioned, right, to attract top talent to lead this effort nationally and internationally. And this fits within the context of what's called the Materials Genome Initiative. This is an initiative, I don't know, perhaps you're familiar with it, right? It's a multi-agency initiative by the federal government, and these are the logos of all the agencies involved. And the ultimate objective is this, right? To create a new era of policy, resources, and infrastructure that support the US institutions in the effort to discover, manufacture, and deploy advanced materials twice as fast at a fraction of the cost, right? So, so with that, I thank you for your attention, and would be happy to take any questions.
All right. You had the chat up in a few minutes ago, Keely. It disappeared.
Oh yeah, I see here.
Here we go. Javier's got a question. If you want, you're more than welcome to speak.
Right. Yeah. So about the theory, when one implements a theory numerically, one has to be careful with the numerical technique or the numerical discretization that one uses. And so there is one requirement is that you define, okay, so the numerical discretizations, for everybody to understand, has to be such that is random, and you do not favor, numerically artificial nucleation, right? So you want to solve the equations properly, and they should not be affected by the numerical technique. And yes, so you have to be careful with that when you implement this numerically. Oh, that's a very good question by Martin. How do you want to deal with scattering experimental data relative to your deterministic curve? So that's an excellent question. So we are now looking into that, and experiments clearly indicate that there is a lot of scatter, and the scatter is mostly, I suppose that I can share the screen and make the point a bit more clear. Let's go to the scatter. It's a very important point. Okay, so here. So this is a typical experiment. Oops. Typical experiment. Is it gonna work? Yes. Yeah. So this is a typical experiment on alumina, but you can think of this for any material really. So you notice here that as you make the crack size smaller and smaller, there is quite a bit of a scatter in the vertical direction. That means that the critical force at which you're going to nucleate cracks, well, it's not deterministic, it's stochastic. it is well understood why this is the case. So strength, as opposed to Griffith fracture, strength is the macroscopic manifestation. I'll show you a picture of the inherent defects. So this actually is a picture of a ceramic, much like alumina, where you can see that this was done through a sintering process, and therefore you have holes, let's say, in between the grains. So you can, let me point here, right? So you can see that these are random in size, in geometry, and all over the place. So it is because of this that strength is stochastic. So one has to model strength stochastically. So this is a not deterministic surface in stress space. It's actually a stochastic one. And this, you have to inform this from a realistic point of view, right? Even for a given system, we should get a handle on the stochasticity. And certainly that's something that has to be accounted for. And that's work in progress. Definitely, that is a very, very important aspect. The things that we have done so far, if you think about the experiment with the glass beads, the right glass went before the left, even though it's almost symmetric, but not exactly symmetric. And that is because of stochasticity. So we have done things that are very simple, but certainly this needs to be informed with more sophisticated stochasticity inputs. But that can certainly be done. It has to be done. I hope that, Martin, that answers the question.
Thank you.
Have you looked at the inclusions that have different thermal conductivity than the surrounding material, also using inclusions to dump out vibrations? Okay, so you refer to, Mark, do you refer to the fracture problem, the inclusions in the fracture problem? Yes, to confirm. Mark? Okay, yeah, maybe there's some problem with the sound, but I'm gonna assume so. So this is something that we are looking into, the things that I show you. I know. Okay, so what do you mean? Oh, you mean for the liquid inclusions? Is that right? Yes. Okay. So this is yes. Okay. So yes, we have started to look at systems now that are viscoelastic. In reality, elastomers, right, are viscoelastic, and so this is something that we have started right now. We have nothing definite to. Yes, absolutely. Yes. So that, yes, for those applications. So this is something that we have started to do right now, and we have some preliminary results on accounting for dissipation, both in the liquid within the inclusions as well as in the surrounding matrix. So yeah, that's definitely an interesting direction.
Do you have any other questions?
Jeff, how do you obtain inherent material strength and fracture energy for your theory, given these values are dependent on the specimen geometry, for example, for non-brittle materials like civil engineering? Okay, that's a very good question. So the theory applies to materials, which means that if you are going to deal with a structure like, let's say, made of concrete, where the aggregates are centimeter length scale and the structure is not much larger than centimeters, then that is not a material. That has to be considered as a structure. And therefore, the theory will have to be applied in a heterogeneous sense. So you have to deal with the fact that it's not a material, it's a structure. So that is the case for concrete, right? And then dealing with heterogeneity is an issue that has to be resolved. It's a huge issue that is not resolved yet, right? So again, the thing that we have in place applies to materials, and therefore to systems where you are going to make a structure, and whatever heterogeneity like aggregates or particles you may have in the system are much, much smaller than the size of the specimen. If the size of the specimen is not much larger than those microstructural features, then you have to deal with them directly. Yeah, so going back to Mark, particularly if you add electro-assisted dampening. Yeah, so one of the things that we are doing for the liquid inclusions in two different ways is that we are looking at liquid metal inclusions. And these are very fascinating materials. So they can be tuned with an electric field. And they're complicated because when you use liquid metal, what happens is that you have an interface that oxidizes. And you have essentially an oxidized layer that has very unique properties that need to be understood from from measurements. So that still, right, is work in progress, but it's certainly an exciting direction. So yes, by using liquid metal, we could consider that those applications that you're mentioning.
Any last questions for the professor? I get, I'm out in the field building stuff, right? Just concrete and steel. What timeline? When do you think we'll start seeing? I mean, the picture that the other professor showed up with the steel beam was interesting, but when do you see like a timeline that we'll actually see applications in the field?
Well, actually, for the work on optimization of topology of structural members, I think that the fact that, I mean, this is what she gave me, right? I mean, we're able to 3D print. This is printed in a polymer, right? But certainly, printing metals is a reality right now. Of course, one has to worry about, that the metal that is printed may not be exactly the one that, because the manufacturing process leads to a material that is complicated. But I think that within years, because we have, if this works out and then it will be tested in reality, right? Everything is in place, right? We have all the tools, all the numerical tools that the theory seems to work. We have all the numerical tools. And my hope is that, with a parameterized study to begin with, and to essentially showcase the capability of these things, that hopefully people will start to implement this. I mean, because right now, testing things, right, is possible. Testing complicated structures or making them. So if there is proof, definite proof, not just theory and calculations, but experiments that demonstrate the superiority of certain geometries over others for certain applications, I think that probably we're talking within years, if we manage to have that definite proof, which I think is possible. Maybe I'm overly optimistic because I know people are very conservative, right, when it comes to applying new stuff. But again, I mean, if the experiments and the theory and everything supports, going that direction, I think that, probably within years.
Excellent. Very exciting. Well, I want to thank you, Professor, for your time. It was a great presentation. Keely, can you address the PDHs and how those would get distributed to everybody?
Yep, so I will send out a form to everyone that's on the call and it will have all the information on there for you.
Wonderful. Thank you so much.
Well,
go ahead, Professor.
No, yes, I wanted to thank you for organizing this event, and I hope that you enjoy it as much as I did.
Yes. Well, thanks, everyone. Any closing comments, Keely?
Nope, we're all set. Thanks, everyone. Thank you, Oscar. I really appreciate it. Everyone have a good evening.
Okay, bye now.